So VSEPR theory, Lewis structures, and polarity is what your quiz will be on Friday. VSEPR stands for valence shell electron pair repulsion. States that repulsion between sets of valence electrons surrounding an atom causes these electrons to be oriented as far apart as possible. So always look at around the central atom. If there is one lone pair, then that counts as one area of electron density. If there is a single bond, that also counts as one area of electron density. Double bond, one area of electron density, and triple bond, one area of electron density. Basically, the electron dense regions repel each other while still attached to the central atom. And therefore, you can figure out the geometry of the molecule by looking at its electron dense regions. So if there's only two areas of electron density, we call that a linear molecule. So it would be something like this. Two areas of electron density, 1, 2. If there's three areas of electron density, that's trigonal planar. So here's our central atom, and then we have 1, 2, 3 bonds, 3 areas of electron density. There are 3 different types where there are 4 areas of electron density. So that is your tetrahedral, your trigonal pyramidal, and your bent or angular. It all has to do with if all of the electron densities are in bonds or if some of them are in lone pairs. If there are 4 bonds around the central atom, then we have tetrahedral. But if there are 3 bonds around the central atom and 1 lone pair right here, that's your lone pair, then it's trigonal pyramidal. Or if you have 2 bonds around the central atom and 2 sets of lone pairs, that is called bent or angular. When you are trying to figure out how to draw a Lewis structure, the first thing that you need to do is figure out the available number of valence electrons. Valence. So use your periodic table, count it up. Remember, if there's a positive charge, that's because electrons were taken away, or if it has a negative charge, then electrons were added. Make sure you draw a skeleton structure and pick your central atom. Remember, carbon loves to be in the center. Do not put hydrogen in the center, no. And then make sure if there is not carbon or hydrogen, you pick the atom farthest away from fluorine. Make sure that you connect your atoms by a line. One line signifies 2 electrons. 1 dot is only 1 electron. Finish by making sure that all of the atoms have their full octet. There are exceptions. Remember that hydrogen only takes 2, boron 6, beryllium 4. For all others, there should be 8. Then what you're going to do is count up the correct number of electrons. If it is equal to the available that you got at the very beginning, then you have the correct structure. If it is not the correct number, then you must make a double bond or possibly a triple bond. Okay, so let's draw some Lewis structures. First, we're going to start with H2O water, and we are going to figure out the available valence electrons. So hydrogen is going to provide 1 valence electron. We've got 2 of them. And oxygen is going to provide 6 valence electrons for a total of 8. So when we make our drawing afterwards, we're going to count up and make sure that we drew 8 electrons in our Lewis structure. We're going to pick our central atom next. Oxygen is going to go in the middle, and we're going to draw our hydrogens surrounding oxygen. After we do that, we are going to bond our atoms, and after that we check to make sure octet is satisfied. For the hydrogen here, this line represents 2 electrons, so this hydrogen has 2 electrons around it. It's happy, because remember, hydrogen is an exception to the 8 octet rule. This hydrogen here also has this bond right next to it, so there's 2 electrons around it. But the way that we've drawn oxygen, there is only 2 lines, meaning 4 electrons around it. Oxygen does want its full octet. So to fix that, we're going to draw ourselves lone pairs. So when we are all done, and all of our atoms have their full octet, we go back and count how many electrons we drew to make sure that we used up the 8 that were available. So we are going to have 1, 2, 3, 4, 5, 6, 7, 8. Good. So this is the correct structure. Now from here we need to figure out its molecular geometry. And because there are 1, 2, 3, 4 areas of electron density, 2 of them being in lone pairs, right here is lone pair, and right here is lone pair. This is your bent or angular molecule. We're going to try the same thing with SO4 2-. That is sulfate. So available valence electrons. So sulfur has 6 valence electrons, as does oxygen, and we've got 4 of them. And this -2 here tells us that we need to add 2 more electrons to our total. So that totals up to 32. Then we're going to choose our central atom. It will be sulfur. And we're going to draw oxygen around it and bond it. The last part is making sure that they have their full octets and that we did draw 32 electrons. So sulfur has 1, 2, 3, 4 lines around it. Each line has 2 electrons. 4 times 2, 8. So sulfur is nice and happy. But the oxygens do not have their full octet yet. So we must go and draw our lone pairs. All right, once all these lone pairs are drawn, we have 32 electrons. We're going to put it in brackets and give it its charge because it is a charged particle. This is 4 areas of electron density. So 1, 2, 3, 4. So that means we have a tetrahedral structure. All right, so let's take a look at carbon monoxide. Available valence electron. Carbon has 4 and oxygen has 6, so 10 total. We're going to put the 2 atoms next to each other. There's not really a central atom. If we just bonded them once and then filled up their octet with lone pairs, you would see that you have drawn too many electrons. So that is not the correct structure. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons drawn, but we only have 10 available. So whenever you have drawn more electrons than you have available, that means you need to make a double bond. So you have to get rid of the lone pairs on both of the atoms and make a new bond between them. You're going to end up having to do that another time so that the actual structure will end up being carbon triple bonded to oxygen, and each of them having their lone pairs. This will be linear. The last one here, beryllium dichloride. Beryllium is an exception to the rule. It only wants 4 valence electrons. So available, we've got 2 plus 7 times 2, 16. So we put beryllium in the middle, chlorine on each side, fill up those electrons, and then you should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that is the correct structure. So remember, this one is linear. 1, 2 areas of electron density. Beryllium is an exception to the octet rule. The last part is polarity. With polarity, what you need to do is look at the central atom to figure out if the molecule is polar or nonpolar. So are the electrons evenly distributed, or is it uneven so that there is a negative and positive side poles? So if the central atom has lone pairs, usually the atom, or the molecule, is polar. So if there are lone pairs, and we say yes, we've got ourselves a polar molecule. But if the central atom does not have lone pairs, we said no. You need to look at the atoms attached to the central atom. If they're all the same, the molecule is nonpolar. But if they're different atoms attached, then the molecule is polar. So look at the outside atoms. Outside atoms, if they are the same, it is nonpolar. If they are different, it is polar. So if we were to go back to these structures that we drew before, water, because it has lone pairs, is going to be polar. Water is polar. Sulfate, SO4 negative 2, does not have lone pairs around the sulfur central atom, and all of the atoms around it are exactly the same, oxygen. So that means that it is nonpolar. All right, keep studying.